Greetings, in this one we will be looking at an interesting proof of a formula we sort of used before when we were counting the amount of elements in a power set. And it is as follows. We knew that it's going to be 2 to the n, and what we can make this equal to, and this is the thing we will be proving interestingly here, is that 2 to the n equals to the sum as k goes from 0 until n of n choose k binomial coefficients. So for example, if n is 3, we're adding 3 choose 0 plus 3 choose 1 plus, and 3 choose 2 plus 3 choose 3 until we get to that 3. So we're rising that k from 0 until it equals to n. So if we're adding them, it should equal to the n. And also from the other side, we can know, using thanks to this formula, that 2 to the n is equal to this expression. And now let's see. Thanks to a friend and a big fan of this channel, that he presented to me this interesting proof. So now I'm going to show it here. So basically, we will be using the binomial theorem that tells us how to expand a parenthesis of this type, x plus y and everything to the n. How is that expressed in general? It's going to be equal to the sum from k equals 0 until n of this argument. So n choose k and x to the n minus times x to the n minus k times y to the k. So this formula gives us how to expand such a parenthesis. And because this is very similar to 2 to the n, we can remake the x plus y into the 2, and thereby also change, with that in mind, the right side. And namely what we can do is set, for example, x and y both equal to 1. And then together they will put a 2, and then it will equal to this. So we will also adjust it on the right side. And also make x and y equal to 1, both of them, on the right side. So let's see. So x and y is now 1, so together they give 2. So I have 2 to the on the left side. And now we are very much prepared to directly proving this formula hereby. So here is in how it works. I'm going to rewrite everything and write 1 instead of x and y. So I get times 1 to the n minus k times, and y is also 1 to the k. And this together reduces into 1. So all that is then left in this expression is k equals 0 until n of only the coefficient itself. So thanks to the binomial theorem, we can use it to prove this case. It's sort of a specific case. We can see it as a very specific case that we can find through the binomial theorem, because this is generalized. And then we can use the binomial theorem, if we know the binomial theorem, to directly prove this expression. So that's very interesting. All we have to do is exchange the x and y's for a 1, for example here, so that we get a 2 in this base, in this parentheses, and then the exponent will be n still, so that stays. And then we have 2 to the n on the left side, and we prove it to be equal to actually this sum that we had.